Hi, in the last session, we talked about comparators in VHDL and we learned why these comparators are important in VHDL designing and how these can be used. Now, let's talk about multiplexers in VHDL. We will learn that what are multiplexers and how they can be used in your VHDL designs. A multiplexer is a very basic digital component in digital system design. A multiplexer selects one signal from several input signals and forward that selected input to the output signal. The preferred way to implement a multiplexer in VHDL is by using a case statement. This is a clean and organized method on input selection, and this is very straightforward to manage the multiple input signals based on a selected line. A multiplexer can be designed either as a combinational design or a register process design, depending on your project requirement, of course. So, combinational designs provide immediate output based on the current inputs. However, register process blocks are synchronized with the clock signal for stable timing. You will be definitely using multiplexers very widely, especially for the large design units where the selection functionality is required. So, in this example, we assume that this multiplexer is part of a larger VHDL design, means all these ports are internal signals of a module. But for now, just focus on the logical implementation of this multiplexer. So this multiplexer is a combinational design, and the output of this multiplexer is driven by a lookup table or LUTs instead of a flip-flop. Here is a block diagram of a multiplexer which we are designing. It has four inputs labeled as A, B, C, and G, and one output named as D out, and one select line named as SEL. This select line tells the multiplexer that which input need to be selected from all these input lines like A or B or C or D here and pass that input to the output D out. So let's see the VHDL code for this multiplexer in the next slide. Before we proceed, please note that this example focused on the logical implementation of a multiplexer and thus there is no entity declaration written here. But we consider that this multiplexer is part of some bigger system design where all these input output ports are treated as an internal signal. So this is our VHDL code and it is architecture behave of mux is signal A, comma B, comma C, comma D, colon, integer, semicolon, signal select, colon, integer, range 0 to 3, semicolon, signal D out, integer, semicolon, begin. P0 process A, comma B, comma C, comma D, comma select, begin. Case select is when 0, then D out gets the value of A, when 1, then D out gets the value of B, when 2, then D out gets the value of C, and when 3, D out gets the value of D. When others, there is nothing. And case, and process, and architecture. So first we declared all the signals in the architecture declaration section. Now based on the block diagram, we defined 6 signals for this multiplexer. There are 4 inputs A, B, C, and G, one output D out, and one select line SEL. For this example, all the signals are considered as integer data type. However, these signals can be anything like std logic vector, signed or unsigned, etc., or even custom defined data types as well. Just remember that the input and output signals follow the same data type. Until they are same, you can use any data type. But if they are not matched, your program will not execute. Instead, it will give you the syntax error. Next, we define the process block, where we will write our code for this multiplexer. This is a combinational process block. Hence, all the signals are added in the sensitivity list of this process block. Means signal A, B, C, D, and select. So your process will execute when any of these signal is changed. Note that D out is not included in the sensitivity list because D out will react on the changes of other signals which are input or internal signal. So this process block does not require to read the value of the out. Now we are implementing the multiplexer using a case statement here. So the case statement uses select signal to find out which input signal from A, B, C or D should be routed to the output D out. Next, we listed all possible choices for this select signal. So when select is equals to 0, then input A will be selected and it will pass out to the output D out. The second choice is when select is equals to 1, then input B will be selected and it will pass out to the output D out. Similarly, when select is equals to 2, then input C will be selected and it will pass out to the output D out. Finally, when select is equals to 3, then input D will be selected and it will pass out to the output D out. Lastly, we have used a default condition. You can write any statement which you want to refer as an invalid input. Note that this is mandated to include a default case in a case statement. In this code, the default case is doing nothing. Now, after listing all the choices, we terminate the case statement. Finally, we end the process block and architecture block. So, this process block will implement a multiplexer with a combination output. And the FPGA will use a lookup table or LUTs for this implementation. And there will be no register involved here. Next, let's write the same code for a registered multiplexer, which include a clock synchronization. This is a block diagram of a registered multiplexer. It is same like our previous design, but now the output is synchronized with a clock signal. So there is a flip-flop here. Means we need to write our multiplexer logic inside a registered process block to ensure that the output is synchronized with the clock signal. Now this is the VHDL code for our registered process block and multiplexer. For registered multiplexer, we write our assignments inside a register process block. And the sensitivity list includes clock signal and reset signal. We do not need to write all the signals here in the sensitivity list in case of registered process block. Although you can write, but it will not make any changes in simulation. But if you write this, it can minor affect your simulation speed. So here is your VHDL code for this registered multiplexer design. P0 colon process reset comma clock begin if reset equals to 1, then D out gets the value of 0. Else if rising edge of clock, then case select is when 0, D out gets the value of A, when 1, D out gets the value of B, when 2, D out gets the value of C, when 3, D out gets the value of D, when others, AND case, and if, and process, and architecture. Now we begin the process body with the begin keyword. Next, we handle a asynchronous reset condition first. So when reset is asserted, then the output signal T out is reset to 0. Then we check for the rising edge of a clock signal. Means any assignment written inside the corresponding if-else statement will be executed at the clock edge. And it ensures that the output is updated synchronously with the rising edge of a clock signal. Now inside the register process, we have written the same case statement as before. Means it will select the input line and pass it through the output based on the select signal. Then we terminate the case statement, then terminated the if condition, and finally terminate the process block with the AND statement. So this code will implement a registered version of a multiplexer where the output is synchronized with the clock signal. Okay, so that's it for today. I hope now you are familiar with multiplexer and their designs. So try to design these multiplexer using combinational and register process blocks and for different data types. In the next session, we will be talking about shift registers and we will create our own shift registers in VHDL. And we will also see that how these shift registers works. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video. comment on video, and don't forget to share. Thank you for watching.